Hi, everybody. Thanks for coming to our talk about what really happens during compilation, which is going to be a talk about what your app bundle really contains. Now, the question probably that you might be asking yourself is, why would you even care what's inside your app bundle? And that's an interesting question that I've heard many times before. Also, when I've been working in different companies, people care really much about their source code and they treat it as a very secret thing, rightfully so. But then the moment they compile the app and they have a bundle in their hands, nobody really knows what it contains. It's surely hard to reverse engineer. And if you upload it to the App Store, it's encrypted on top of that. So it doesn't really contain interesting things, right? And that's what we are going to talk about today. My name is Samuel Hopstock. I work at Guard Square in Munich, and I work on two different things. I work on app protection and app analysis. And that's also how this talk came to be, because I was originally working on the Android part of our app analysis product. And then when we wanted to expand into the iOS world, I was tasked with setting up the infrastructure for that. And so I came from a very easy use case in Android Studio, where you can build your APK. It gets dumped somewhere in your build directory. And inside the APK, you have your binaries, you have your Java bytecode, and all the resources. And so I thought, yeah, if I am now supposed to analyze iOS apps, surely it's going to be exactly the same thing, right? And then I arrived in Xcode and it told me something about signing, and I didn't really know how that all works. And it took me surprisingly long to get something to build. But unfortunately, even signing alone would probably fill an entire afternoon. So we are just going to skip that part very briefly. What are we going to talk about? What exactly does your bundle contain? How is it structured? Inside your bundle, you will have your compiled code inside a Mach O binaries. And what is the structure of that? How can you tamper with your app and your binaries? And then in the end, we will also talk about some strategies that you can take to mitigate that tampering if you feel like this is an attack vector you want to prevent. So what does your bundle contain? On iOS and also macOS, an app is bundled in a .app directory. If you open that in your file browser, it actually looks like a file, which it's not really true, because it is a directory. It's just how macOS displays that in the Finder. And it contains a bunch of resources, similar to how I showed the APK contents previously. And then there's two ways how to package that. One is the xcarchive that you get when you press archive in Xcode. And xcarchive really contains this app bundle in the product's applications directory with dsyms. We will look at what dsyms contain exactly later on, and some metadata in the Info.plist file that contains bundle information that you need for creating an IPA later on. And that IPA is what you actually upload to the App Store. It also contains the app bundle just as it is in the xcarchive, but the dsyms are gone. And instead, you might have a symbols directory with cryptic.symbols files that basically have the same content as the dsyms, just in a proprietary format for Apple. Now, if you look a bit deeper into what the bundle contains, we can go hunting for some metadata in the app. And the first thing that you would do, coming from a reverse engineering point of view, you look at the Info.plist file that contains information that might be something you recognize from all the different Xcode build settings you can do. You can set your bundle identifier that ends up in the Info.plist, the app name that will be displayed to the users on the home screen, the minimum OS versions, for example, also other configuration options, like you can set different keys for allowing HTTP traffic, which is in this case called NS allows arbitrary loads. If you see something like that in an Info.plist file as an app analysis person, you can get a bit suspicious already, because this is something you should not be doing nowadays, supposedly. But yeah, you can collect a bunch of metadata about the app in there to see if there are some entry points you might be interested in later on. For example, this app has a custom URL handler, and you need to declare that in your Info.plist file. If we go on to another file that's called embedded.mobile provision, that contains signing information. As I said in the beginning, signing is a very important part of the Apple ecosystem, and you surely know that as well. And that information is embedded inside your app bundle. So you can see things like the team name that was used to sign this application, the bundle identifier as well, and other metadata like which platform is this app supposed to be signed for. In this case, for example, for iOS or XROS or visionOS, you can use the same signing certificate. And apart from that, you also have various resources that the app needs at runtime. For example, in the .lproj directory, you find files related to language settings, like translations of hard-coded strings that you might have somewhere in your storyboards or now in Swift UI as well. You have third-party frameworks. Those frameworks can either be statically linked directly inside your main binary, or they end up in actual .framework bundles inside the frameworks directory. And then each framework bundle by itself has a main binary that it will use to execute the code. It has a code signature, metadata, and also an Info.plist file, just like your app has as well, containing things like the name of the framework, the version, and also minimum OS versions and things like this. Now, if we look at the actual binary and not just the other things that you have in your app bundle, that binary is compiled using the Swift compiler and Clang, depending on the language that you're using. Swift compiler is obviously compiling Swift files. And the interesting thing here is also that those two compilation strands interact very much with each other. Because if you have Swift files that use Objective-C code or Objective-C files that interact with Swift code, you will generate bridging headers in the compilation stage, and then it's not a straight line anymore, but they actually interact a bit depending on the order in which they are compiled. Then, after compiling the file to object files, the linker comes and makes sure that it declares which external functions from frameworks or the Apple SDK you're using and produces the final executable and the dsym file. The dsym file contains debugging information like line numbers, file names, and also where your functions are located in the binary, because technically that information is not needed for execution. But if you want to debug your app, you want to know, if I set a breakpoint at this location, when do I hit it and how do I then step through it? The main binary itself is structured in the so-called Mach O format. That is the same format used for all Apple platforms. And the code inside that binary is structured in different segments. Those segments contain different types of data. For example, the text segment contains the actual executable code. Then if you have constants and variables that you use globally, they end up in different segments. And this is how the file is structured on a high level. And each segment can then contain individual sections. And I put some interesting section names there already to peek into the next few slides, because the interesting ones are going to be the Objective-C underscore sections and the Swift underscore sections, because they contain a lot of metadata that the system needs at runtime. And that is also metadata we can take a look at statically if we want to get information about the application. So if we take some really easy Objective-C sample code that creates a class with one property, and we compile that to a binary, we can see what information it gives us. At first, if we look at the actual symbols inside the binary, symbols are just names for functions and variables that you use. We don't really see a lot. We just see external symbols that you import from the runtime, some Objective-C underscore whatever symbols. But the class that we created is nowhere to be found. And the reason for that is that in a release binary, you don't have this debug information, but it explicitly lets split off into the dsym files that I mentioned previously. Now if we take a look at what the dsym bundle contains exactly, it contains in the dwarf directory, it contains an actual binary containing debug information, and you also have metadata in the Info.plist file and information about relocations that the linker needs to resolve certain things. And inside that debug information, then we finally see the myClass reference to the setMyProperty method that would be generated if you have a property with a setter. And it tells us which line it was declared in which file, and also a lot of extra interesting information about the parameters of the function and what type they have. Now, the good thing about dsym files is that they are entirely private to you. They will never end up anywhere in the IPA that the user downloads from the App Store, which would have been an issue otherwise if you want to keep certain classes secret. But since this is not shipped, this is really not a problem then. But what is shipped is actually the binary itself, and that contains metadata, as I mentioned in this overview of the Mach O format. And we can dump this metadata using a nice tool called IPSW, and you can just ask it to dump the classes. And the output of that is really close to what we actually set up in the sample code. You see the class myClass, what it inherits from. If the inheritance structure is a bit more complicated, you would also see that in here. The name of the property, the name of the functions it has. And the reason why this exists is that Objective-C is a very dynamic language. And as such, you could, for example, add methods at runtime. You could rewire methods so that they call other actual code when you call them, or you could delete methods from your class. And for that reason, the Objective-C runtime needs all this information that we just saw, all the class names, the property names, the selector names for functions. And when you compile Objective-C code, every call to a virtual method of your class will end up as an actual call to the Objective-C message send function. And you just tell it, I want to please call the setMyProperty function, and then the runtime is supposed to figure out where that function is located and invoke the function directly. And if you look at the binary, it really has a lot of structure in the metadata, and you can parse it all. If you, for example, are interested in figuring out which classes you have in a library, which classes you have in an app, and things like this. And the runtime really needs that, so there's no way to actually remove this metadata safely. And you would have to find other solutions to the issue of having classes in your app that might be sensitive to be revealed to users of your app. If we do the same thing for Swift, same class with the property name and a setter function, we again don't get any of that information in the symbols itself. And if we dump the Swift metadata with the Swift dump command of IPSW, we again get pretty much all the information that we had previously, with the difference that Swift doesn't always need to know about names of methods, because Swift method calls compile directly to calls on the assembly level and don't go through any runtime. But Swift still uses reflection and is interoperable with Objective-C, so some part of the metadata that Objective-C has also needs to be there for Swift. The last part that I want to talk about for binaries specifically is how do you figure out which external functions they are calling? And that is used by a mechanism called the global offset table, or GOT for short. And you can just register certain library names and function names, and the linker will then take care of it for you and create the GOT for you. And this table will then at runtime contain the address of the functions that you want to call from external frameworks or from the Apple SDK. And having this in a table is a very practical thing for the compiler, because the compiler really just says, if I want to call function foo1 that I don't know where it's going to be at runtime, I just call the address at this offset in the table and everything will be good. But if you have all this lined up in a table, that gives you the chance as an attacker, if you want to change the behavior of an app, to rewrite those entries of the table. And that brings us to the next part of my talk, which is how do you actually tamper with apps if you want to change their behavior at runtime? And this GOT hooking would be one technique where you say, I have my own framework that I inject into the app, and inside the GOT, I just change the entry that the app will call at runtime to point to my code, and then I can just do whatever I would like to do when somebody from the main code calls this function. You can also directly patch functions inside the main binary if you feel like this. This is called inline hooking. And usually what you do, for example, tools like Frida do this, that when somebody calls a function, they will replace the first few instructions of that function with a call to an external injection function. And then that function executes the code that the attacker would like to execute at this point, jumps back to the original code, and then we can continue as usual. You can also directly patch the bodies of functions, but that might be a bit more tricky in case you suddenly end up using more instructions than the original function would be using, and then you would start overwriting other code that doesn't belong to that function. That's why usually patching the first few instructions and being very minimal in your tampering is easier for attackers. And since Objective-C is also a very dynamic language, as I said, you can just add functions at runtime. You could reroute functions. And that is also something that an attacker could do. They could say, whenever the Objective-C selector foo is called, please just call this function body from now on and not the one that was originally registered by the app. And there are some tools that you can use. For example, if you work more in a jailbreak environment, there are real SDKs you could use that you can ask, hey, I want to hook the function with this name, with this content, and the framework will take care of it for you to select which hooking method it should use. What you can also do, if you don't want to change the behavior of an app at its runtime, but for example, you want to distribute an app with extra cheats or extra features to other users, you could get the IPA from your device, unpack it, change the contents of that bundle, like I showed it before. You could remove the main binary and put your own binary in there. You could add extra frameworks. You could change Info.plist values. And then you just zip it again and distribute it to your users. And that is very often done for correct premium content. For example, if somebody has a check in there that if you did purchase something through in-app purchases, then you should be able to use certain features. And if not, it aborts the use of these features. And if you patch out this check inside the binary, you could distribute your app now as the premium version of the other one without having to pay for it. And there is a market for these sorts of things. Usually it's really about games, getting free gold or getting extra lives. Or if somebody doesn't want to pay for subscriptions for YouTube Premium or Spotify Premium, that is also something that users usually like, and they will look for these sort of repackaged applications on the App Store. And how do you really do that? As I said, unpacking the IPA that you get from your device is pretty easy. It's just a zip file. And when you then modify any of the binaries or resources, you could use the same patching techniques that I outlined previously in the runtime approach and just patch the function body that you want to patch and put that patch binary in the new bundle. You could patch out security checks or any of the premium content I mentioned before. Sometimes, for example, with YouTube, that's a very popular approach of adding extra features, like being able to block certain parts of videos that contain sponsors and things like this, or removing ads, of course. And then when you rezip it, you have the issue that you need to sign the app, of course, because that is the whole point of signing IPAs in an Apple landscape. The signing means we hash the entire content of the bundle, and this cannot be changed without breaking the signature. But the thing is, it doesn't matter which signing certificate you really use. You just need one that is valid for the bundle identifier you're using. And that bundle identifier is also part of the app. So you can find ways to change the bundle identifier to one that you own and then re-sign the code, even if it's not your code at this point. Distributing and installing an app is a bit more difficult than it is, for example, for Android, since on Android you can just upload the APK somewhere to a website and people will surely find it and download it. But on iOS, that is also starting to change now with the extra app stores that Apple needs to allow, or you distribute it to your users directly and they should then sign it with their own developer certificate if we're talking, for example, about cracking premium apps. That's something that users will definitely want to do, and they will also then start signing the app if you tell them so. What you can do against this is that you put checks inside your own app that check, for example, if the content of the app is still the same as it was when you published your code, and don't just rely on the actual signature check from Apple, but also enforce that the signing identity that signed the app is yours. Or you could uh, start detecting if somebody attaches a debugger or if your function body doesn't look the same as it did anymore, and try to mitigate attacks this way. Now, if you add these checks to your app, since the user could replace any code of your app, they could also just look for these checks and replace the checks with their own code and remove it again. And that's why you always need to think a bit about how you make those checks a bit stealthy to not find them anymore, or to also protect your checks with other checks again. What you can also do is that whenever you have checks inside your app to check the integrity of the device or the integrity of your app, that you monitor what's happening and you don't necessarily want to crash the app or tell the user that they can't use the app anymore, but you can just monitor to see if you actually have any attacks and if that is something that's relevant for you. And then you can decide later on if you need to change the behavior of your app, or if it's fine for you to tell the user um, to use your original version if it's not something that they got for free instead of for paying. But protecting the app against malicious users is not really the only thing you should do, because if you write insecure code, like for example encrypting data or handling user data in an insecure way by sending it to the internet or sending it to third-party frameworks, that is something that you won't fix by just obfuscating your code and inserting integrity checks. You really need to make sure your implementation is secure. And OWASP has a really nice project nowadays. It's called the Mobile Application Security Verification Standard, with the Security Testing Guide as its counterpart. And in here, they have a list of things you should check inside your app. And you should check, am I actually vulnerable to these scenarios that they're outlining here? And if so, they have good recommendations of what you can do to fix it. And you can follow that list manually. You can also use automated tools to detect these sorts of insecure coding patterns and, for example, integrate it in your pipeline. Or a very classic approach is also using a pen test after you are done with your app, with the app's latest release, and verify that it's good to go to the App Store. So in conclusion, I would say that you should just be aware of what you ship inside your app and then decide, is any part of what I ship an issue for what I consider attackers, which might be very different for open source apps or for apps that handle sensitive data, like using custom ML models that you want to deliver to the device. Then you suddenly have very different security requirements, and you should be aware of what those are specifically for you. And then when you are at a point where you could define your attacker model, you should also think about the entire life cycle of your application, how you can make sure that you are handling it as securely as possible. And the easy way of doing that, of course, is integrating that into your CI so that you don't have to pay for a pen test every time you want to check it, but you really get notifications about important changes when you do those changes to your app. And one thing we could also think about is, if it's not just your app, but it's an ecosystem where your app communicates with a server. Imagine you have an API on your server that is very expensive for you to run, and you want to verify that it's really your app in an untampered state that it's connecting to that server, and otherwise you want to prevent that from happening. You could use something that you can call app attestation. but unfortunately, that would be a bit too much for today. So if you want to talk about attestation or any other parts of security, you can visit us at our booth and have a chat with us. So thank you very much for your attention.
I think one thing that I'm curious about, when you are looking at Objective-C code that's been decompiled, you can sometimes see some very funny names for methods because it doesn't obfuscate any of the method names. I'm particularly thinking of there was a thing in core data for years that was like sadness is the depth of the death of optimism. Have you seen anything like that where people are either sort of letting a little bit too much information go about the programming process, or sort of giving you more of an insight into like what is happening there?
So one thing that we sometimes see, and that's very interesting because you see that the point of maybe preventing people from patching out authentication checks, for example, is something the developers thought about. When you then see a big method name like is device jailbroken, then you think, okay, this is uh, understandable that you may want to do that, but they probably then forgot that they should not name it that way if they want to have that in their app. Sometimes what you do also see is that you have very gibberish function names because there are tools that can actually encrypt those function names for you or obfuscate them statically. Um, but yeah, you can see a lot of interesting names really if you look at an app.
Cool. Let's see. You mentioned the OWASP uh, stuff uh, around the security. They have like they call it like the OWASP top 10 that I feel like a lot of corporate things are very interested in. Do you feel like those are like a good place for people to start, or do you feel like those are sort of more advanced?
So specifically, the OWASP top 10, in my opinion, are not really that good for mobile apps because they tend to be very web centric, and you have more things that if you develop an app, you don't really care about certain parts of that, and that's why actually they started this mobile specific program with the MSVS, MSTG, and those are really interesting to read. And also the team behind that, in my opinion, is doing a really good job to make sure that you understand what they try to tell you with why is it actually insecure and in which situations is it insecure because it might not be relevant for your app, and they really then explain to you how to check for it and determine if that is an issue for you.
Okay. The other question you mentioned, pen testing, so penetration testing, basically when somebody tries to break into your app.
Yes.
How do you like qualify people who are doing penetration testing? Like how do you basically like know that someone is actually a white hat hacker, and not just like a jerk trying to break into your app?
That is a good question and probably not something you can answer. I mean, there's a bunch of certifications you can do in the industry, I suppose, but anybody can do those, even if they don't really want to help you, but just want to find things in your app. So I don't know if there's any qualification that you could do to determine if a pen tester is doing a good job or not doing a good job. That's a bit hard to say.
You think it's just more like finding recommendations that of other people who
Exactly. I think if you find somebody where somebody told you they have good experience with that person, then that's good. Or same with tools. You don't really know if a tool is going to give you good results or not. You just need to try it for a while and see if you see things that make sense, and then continue using that tool or get recommendations.
Okay.
We've got quite a few questions from the audience. I'm trying to group them. One main theme is around like how can we defend against repackaged apps? So is the App Store doing anything to detect them? And are there any kind of identity checks that we can do either inside the apps or on the backend that the apps are talking to?
So if you want to do that on the backend, that would go in that direction of app attestation that I was talking about, because what you can do, and that's unfortunately something that Apple, I think they start doing something like that, but they don't really have that yet, where you can check from inside your app, is the hash and the identity that signed me still the same? Is the environment correct? And then just send that information to the server and don't really take any decision on device. And then your backend can then decide, is that something that we expected? Is that looking like a repackaged app? And then you can deny access to your APIs, for example, or just not let them log in.
And I guess that depends also on how critical the
Exactly. Like if
APIs
you
are.
if you have an open source app that only displays a bunch of images, you don't need these things. But then I think, for example, in the food delivery industry, that's a big thing where a lot of repackaged apps are floating around, and that's something that you then should prevent with these sorts of checks.
And on the topic of also security, what's the best approach, if any, to store secrets into the bundle of an app?
That is a very interesting topic in my opinion, because, for example, the Google API keys are telling you that if you specify it on their website, only your app can use it, and I think you specify your bundle identifier. And the question then is, how does the API actually check that? And unless you use something on device to really tell the backend this is actually the bundle identifier, not just a string I added to my API request, it's hard to do that. And that's why storing API keys in the bundle should probably only be done if you would be fine with publishing them anyway. Because if you put them in your bundle, anybody can have them. There are techniques where you can encrypt them at runtime. Certain application services don't do that, like Google API doesn't want you to encrypt the key in any way. And yeah, then you are looking at a hard problem again, that maybe if you use something like attestation, you could move that API key to the backend, and then you don't have to ship it in any way.
Yeah, and we had a question specifically about the Firebase Google Service
Yes,
Info.plist.
yes.
So from what you said, there are some specific mitigations, and it's not because Google says it's fine to put that in the bundle that it's fine to put any API key in the bundle.
Yes, and Google specifically, I think, actually still nowadays says it's very fine. You can just put it in there as long as you prevent it on the backend by ticking a checkbox. But I'm not sure how they would really tell if it's not an attacker script that just adds that bundle, because finding out the identifier is an easy thing to do. And so yeah, I would not put it there, but then that depends on what API provider you use, I suppose.
Yeah, absolutely.
Mm.
And one other question is it possible to do the kind of runtime tampering that you showed on a device that isn't jailbroken?
Yes, I think there are things like Troll Store, for example, where the idea is that on certain iOS versions, you can actually re-sign apps dynamically without having to have jailbreak access. And then you can do these sorts of things. But typically, if you are not in a jailbreak scenario, then you are talking about repackaging, and then that's the way to tamper with apps. Because dynamically, you do need some sort of elevated permissions to do that.
Yeah.
And I think that's all I had.
I just have one more. Do you have any recommendations in terms of tools for obfuscating names if you decide that that's the way you want to go to make sure that people can't grab the names of your functions?
I mean, obviously, our company creates those tools, so
Seems legit.
so there are a bunch of also other companies that create these things. So there is an industry for that. Um, I think what it mostly depends on is the approach that these tools take. Is that something that, if you look at that, how do they encrypt things? Because, for example, if you encrypt certain sensitive strings, you should also make sure that they are then re-encrypted after you use them. Because if they are in memory after using your app for a while, are they really protected as they were in the beginning? So that's a bit what you need to think about when comparing different tools.
Awesome. So good. Well, thank you very much, Sama.
Thank you for having
Thank
me.
you.
All right.